Question 5c. Dr. Cool wishes to find the temperature of a very hot substance using his thermometer, which only measures up to 100 degrees Celsius. Dr. Cool takes a sample of the substance and places it in a room with a surrounding air temperature of 20 degrees Celsius and allows it to cool. After 6 minutes, the temperature of the substance is 80 degrees Celsius, and after a further 2 minutes, it is 50 degrees Celsius. If capital T of T is the temperature of the substance after T minutes, then Newton's law of cooling states that capital T satisfies the equation d capital T dt is equal to K times capital T minus A, where K is a constant and A is the surrounding air temperature. Part 1. Verify that capital T equals A plus B times e to the power of kt satisfies the above equation. In keeping with the current syllabus, I'm going to apply techniques in solving differential equations to come up with the solution capital T equals A plus B times e to the power of kt, rather than verifying the solution that's already given in part 1. So we're going to solve the differential equation using separation of variables. Now in this line here, I've combined two steps in one. The first step is to separate the variables. So we have the differential d capital T over capital T minus A is equal to K times dt. And in the second step, I'm going to integrate both sides of this equation. So what you do to one side, you do to the other. Now the integral, the left-hand side, is ln of capital T minus A. And the integral on the right-hand side is kt plus the constant of integration c. Raising both sides of this equation to base e, we have capital T minus A is equal to e to the power of kt plus c. Now adding a to both sides of this equation and also separating this term here using index laws, e to the power of kt plus c can be written as e to the power of kt times e to the power of c. And of course we're adding a here. We have capital T is equal to a plus e to the power of kt multiplied by e to the power of c. Now c is a constant. E to the power of c will also be a constant. I'm going to allocate b to represent e to the power of c. So therefore, capital T is equal to a plus b times e to the power of kt, and this is a solution to the differential equation. Part 2. Show that k equals negative log base e of 2 over 2 and find the value of b. The following are the marking guidelines for question 5c, part 2. For 1 mark, we have substitutes both initial conditions into the equation or uses one initial condition and the given value of k to find b. For 2 marks, we have obtains one value by legitimate means or uses a correct method with a single mistake. So for example, capital T equals 50 at time t equals 2, leading to k equals log base e of 2 over 4, and b equals 15 times the square root of 2. And for 3 marks, we have the correct solution. The first thing to note is that as time t approaches infinity, the temperature capital T approaches the room temperature of 20 degrees Celsius. And that's because b times e to the power of kt approaches 0 as time approaches infinity, and also because the growth constant k will be negative. The substance is a very hot substance cooling from whatever high temperature it's at, cooling down to 20 degrees Celsius. So k will be negative, and e to the power of negative infinity is equal to 0. Hence, a is equal to 20. Next, we're going to find k by applying the boundary conditions, and there are 2 boundary conditions. We have the temperature at the 6-minute mark is 80 degrees Celsius, and the temperature at the 8-minute mark, so that's 2 minutes later, is 50 degrees Celsius. I'm going to form 2 equations. So we have 80 is equal to 20 plus be to the power of 6k. We'll call that equation number 1. And we have 50 is equal to 20 plus be to the power of 8k. We're going to call that equation number 2. And we're going to solve these 2 equations simultaneously. Just to simplify things, we're going to subtract 20 from both sides of both of these equations. So we'll have 60 is equal to BE to the power of 6k, we'll call that equation number 3, and 30 is equal to BE to the power of 8k, and we'll call that equation number 4. Now, taking equation number 3 and dividing it by equation number 4, that eliminates the b, and we have 2 is equal to e to the power of negative 2k. Taking the natural log of both sides, we have ln of 2 is equal to negative 2k. And dividing both sides by negative 2, we get k is equal to negative half times ln of 2. Now, using either equations 3 or 4, I'm going to use equation 3 in this case to find the value of b. And now that we have the value of k, I can make b the subject of the formula. We have 60 divided by e to the power of 6k, and we can substitute the value for k that we just found. And we get b is equal to 480. Therefore, temperature T is equal to 20 plus 480 times e to the power of kt, where k is equal to negative half times ln of 2. Part 3. Hence find the initial temperature of the substance. Now that we have the equation from part 2, which is the temperature T is equal to 20 plus 480 times e to the power of kt, where k is equal to negative half times ln of 2, we can now find the initial temperature. So that's the temperature of the substance at time t equals 0. So temperature at time t equals 0 is equal to 20 plus 480 times e to the power of 0, which equals 20 plus 480, which equals 500. Therefore, the initial temperature of the substance is 500 degrees Celsius. The following is the feedback from the Marking Centre for question 5c. For part 1, this part was generally well done. Candidates only needed to verify that capital T equals A plus B times e to the kt satisfies the differential equation. Those who integrated were not always successful. For part 2, the neatest and most economical solution changed the time frame to t equals 0 at capital T equals 80, arriving at the value of k most efficiently. Candidates who did this were then able to adapt the conditions to answer part 3 correctly. Using a definite integral was a rare but also neat approach. Many candidates thought the initial temperature was 100 degrees Celsius. Some defined after a further 2 minutes as t equals 2, even though they had started at t equals 6. And for part 3, nearly all candidates recognized that initially means t equals 0.